continue where we left yesterday. And I think yesterday we were just covering examples on good conductors and low loss dielectrics. So that's what we covered yesterday, the last session. So with good conductors, we had a couple of approximations, and those approximations I suggest to all of you to obtain those from the general expression of alpha, beta, and the impedance. Okay, so try to extract them from there because it will serve you in the long run to understand the equations much more easier. So having a look in those, let's see for a moment. Okay, so let's go over one example again, and after this example, we'll start to discuss the Poynting theorem. So let's assume that we have an electric field component, or the electric field of an electromagnetic coupled wave. So EZE, which apparently this seems to be the instantaneous expression, because once we have also the time, this would be called the instantaneous expression, and this is equal to AX E0, the amplitude, times e to the power minus alpha z, okay? So the moment that we observe this e to the power minus alpha z, what do we understand here? We observe that we have an attenuation, okay? We have an attenuation of the wave as the wave is propagating along the plus z direction. Then here we have cosine of 6 pi times 10 to the power 3t minus beta z, okay? So this would be this is the wave, and this wave is propagating into water, okay? So let's say that, and here, the parameters, we have that the frequency is 3 kilohertz, sigma is equal to 4 Siemens per meter, epsilon r is 81, and mu r is 1. Okay, so these are the parameters that that are provided, and the first thing that we might always look into is this expression. It's the sigma over epsilon e. Okay, so these 4 parameters that we are given, we should immediately try to figure out in what range or in what domain this material is. So here, just if we judge based on the order of the quantities. So here we have 4 divided by 2 pi f, okay, so this is equal to sigma divided by 2 pi f, okay, times the permittivity. And this permittivity is, we have to multiply it with epsilon 0, because here we have an 81 times 8.85 times 10 to the power minus 12. So once we look at this expression, this looks like this, when we divide this one by 8 to the power minus 12, this looks like this is a huge loss, effective loss. Okay, so it's a very lossy material, because this is a factor which is much higher than 1. And let's not forget, we used to call this one also the tangent of the loss angle. Okay, so given these, the answer is something like 3 times 10 to the power 5, 3 times 10 to the power 5, which is much larger than 1, okay? So the first thing we needed to figure out is this. So it looks like this is a good, very good what's the name? Conductor. So if this is a very good conductor, what do we know? We know a couple of things, which is alpha is going to be equal to beta. That's what we know for now. And we have also the expression. And we know that beta c is going to be equal to the magnitude of this impedance times e to the power j 45 degrees. Okay. So whenever we are in input on conductors, without substituting or without finding all the numbers, this is for sure. Okay, so we expect these values. But now let's see what is alpha and beta. Alpha and beta, they are omega mu sigma. So these numbers are omega mu sigma divided by 2. This is a square root. So omega is equal to 2 pi times, wait a second, the frequency is 3 kilohertz. So here we did not substitute this, but here we have 3 times 10 to the power 3 times mu, and mu is equal, mu in this case is equal to mu 0, because mu r is equal to 1, so we have a non-magnetic material. This is 4, wait a second, this is 4 pi times 10 to the power minus 7, this is the mu, times sigma, which is another 4, times sigma, divided by 2, and then, as a result, let me see, is this all right? So here we have 2 pi mu, this goes away, and we have here 3 times 3 is almost 10, this is 10 to the power, so let's see, this is 10 to the power 1, this is another 10 to the power 1, which makes 10 to the power 2, 10 to the power 3, this is 10 to the power 5, so up to this point, this is 10 to the power 5, times 4, this is almost 10 to the power 6, 10 to the power 6, times 10 to the power minus 7, we get a number approximately 10 to the power minus 1, okay? This is the order of magnitude that we can get from here. And we get the square root of this. So it looks like the alpha and the beta is something between 10 to the power minus 1 and 10 to the power minus 2. If we substitute the numbers correctly, we get something like 0.22. And this is the magnitude of alpha and the beta. Now, once we have this, the next parameter that we can easily distinguish or figure out what they are, we get the lambda, which is 2 pi over beta, okay? So this is the lambda. The lambda then is going to be 6.28 divided by 0.22, okay? And the wavelength is going to be something in the order of meters, around 29 meters. Okay, so this is here we have 29 meters for the wavelength, and then we may want to figure out also the phase velocity or the speed of propagation. So the speed of propagation UP, we can denote this one as lambda f. Lambda f. This is the relationship between, because lambda is measured in meters, frequency is measured in inverse seconds, so we get a speed. So this is going to be equal to 29 meters, the wavelength, times 3 times 10 to the power 3. So this is the propagation speed, which results in a number of 8.6 times 10 to the power 4. Okay, so this is the speed of this frequency in this specific medium. And this is, when we compare this with the speed of light, this is something around, it's c divided by So we lose something like 3 orders from the speed of light, where this is 3 times 10 to the power 8. Okay, so this is the speed of light. Another important parameter, it can be the depth of penetration, which is equal to 1 over alpha. If this is 1 over alpha, this is going to be 0.22. And or the skin depth, this is something like 4.6 meters. 4.6 meters. So if this is 4.6 meters, what was the wavelength? The wavelength, it was 29 meters. Okay. So if we try to visualize this, let's assume that this is water or ocean water, and the wave is coming downwards like this, and this is the time harmonic oscillatory feature of this electric field. Okay, and this one, and by the way, let me just check one thing. The microphones are set. Okay. So this wave that is coming down, and the electric field of this wave, which is going to appear like this, is propagating all the way down. And let's figure out, this is 4.6 meters. 4.6 meters, let's assume is this quantity. So this is the skin depth that we denoted like this. Now, once the wave comes down like this, we see that the wavelength is 29 meters. How can we show this? This 29 meters, this is, assume that this is something like around 5. This is 6 times higher, okay? Which means that, wait a second, yeah, 5 times 6, that's exactly what it might be. So with this skin depth, we might expect 1, 2, 3. So the wavelength, of course, the wavelength here, it might be different. This is not to scale. What is to scale is the ratio between this wavelength, because we know that the complete wavelength is when the wave completes the 2 pi cycle. And as we said, this is approximately 4.6 or approximately 5 times 6. So we have 6 of these units to complete one complete wavelength. Now, what do we understand from here? From here we understand that this wave is being attenuated too fast, okay? It is so fast that almost 60% of the energy of the wave is lost right here, okay? So before completing its complete wavelength, the wave is attenuated considerably, and this is the reason because we are dealing with a very good conductor. So if you look at these numbers for the loss tangent, so either this or this, these are all anything to the power 10 to the power 5, and that's why we have this configuration. But it should be good to understand how that figure, how we understand that figure. Now, let's write also a couple of more parameters. So this number that we see here, the impedance is going to be equal to, so impedance is a complex number, and this is equal to mu omega divided by sigma times e to the power j 45 degrees. If we substitute the numbers, this is going to be something like 7.7 times 10 to the power minus 2 times e to the power j 45 degrees. Okay, so this is the impedance. With this impedance, I think we can erase this because we know what this was. Okay, now that we know the impedance, we can find the H, and H, the instantaneous expression for the magnetic field intensity, it's going to be, so first of all, let's see, along which, so what would be the direction of H? What is the direction as a vector? Who can answer this? So what is the direction of the, we know that E cross H, this is equal to the propagation direction, okay? So in this expression, what is the direction of electric field? This one is AX, okay? Cross product with H, we don't know what H is, and this is going to be equal to AZ. Because the wave is propagating along the positive Z direction. Okay, so if the wave is coming this way down, this means that this is the positive Z direction is pointing downwards of the wave. So it looks like this is going to be equal to AY. So the direction of H, this is AY times, then we have this coefficient of the electric field intensity divided by MC. So here we can write E0 divided by this magnitude here, okay? And then we have also to multiply e to the power minus alpha z, and this phase angle here, so let's not forget, before we divide by this, we're going to have here e to the power j 45 degree. So dividing by this parameter, we'll get this up in this form, and this will be cosine of 6 pi times 10 to the power 3 e minus beta z minus pi over 4. So this 45 degrees is this. So initially we divide with this because this is the intrinsic impedance, and once we divide with this, but actually these divisions by this complex number, this appears only in the phasor notation. Okay, when we come to the instantaneous expression, this phasor notation, so this term, it first appears in this term, which is going to be e to the power j omega t minus beta z, okay? And this was divided by e to the power j pi over 4. So we are still in a phasor notation. We pick this up, which is going to be that this becomes minus pi over 4, and then when you take the real part of this phasor to obtain the instantaneous expression, which includes also the time, the real part of this will be the cosine, which appears in this form here. Okay? So we understood here what is the direction of magnetic field, and also how the magnitude of this is going to change. So based on this, let's see, this is going to be the H. Now, let's say that we have an antenna here, okay? So the antenna is propagating the waves over the sea level, and the wave is propagating downwards, and here at the bottom we have a receiver, okay? This is a receiver, and this receiver is a very good one. It's a good receiver that can measure microvolt per meter. Okay, so we can say here sensitivity of this product, it is 10 to the power minus 6 volt per meter. It's a good one. And then if this receiver, which can measure microvolt per meter, so it's a good oscilloscope, you could call this. Let's say that this is at a depth of Z equal to 100 meters. Okay, so we move down 100 meters into the seawater, and we have a submarine coming in which is going to measure, is going to pick the communication signals, or is going to pick this wave. So the question is, what can be E0? So what is E0? Which is called the amplitude, initial amplitude, if at Z equal to 100 meters, we can pick up 10 to the power minus 6 volt per meter. Okay, so this is the question. we need to find the E amplitude, and for this, we can say that initially we have here that E, this term, so this term in red, e to the power E minus alpha z, this is going to be equal to 10 to the power minus 6. Okay, so this is how this will be attenuated. And then this E0 times e to the power minus 0.22. This was what alpha was, times 100. This becomes like E0 times e to the power minus 22. This is equal to 100. So this e to the power minus 22, this is extremely large value of number, okay? Sorry, this is like this. No, this is not, this is 10 to the power minus 6, okay? 10 to the power minus 6. And then we find out, so if we divide this 10 to the power minus 6 with this value, we find that E0, this is equal to let me see, it's a 2.8 kilovolt per meter. 2.8 kilovolt per meter. So this is a very large, a huge wave intensity, okay? Oh, and this wave, it carries a lot of energy, because we know that when we communicate from an antenna to a receiver, when we send the waves in vacuum, we know that we have some energy density, so the wave is carrying some energy. And if you remember from the previous courses that you have taken, you remember that there is an energy term, I can write this like this, which is proportional to epsilon E squared, okay? This is some energy density, which is measured with joule per meter cube, and this is relatively large. Now imagine for a moment, if you use this electric field, this electromagnetic field, which has a field intensity like 2.8 kilovolt per meter, once you insert this here, this is an indication that you are generating a lot of energy. And this energy of the wave, so this is energy, let me write this is energy. This energy of the wave, this carries momentum. I'm writing momentum like this because we have seen this in physics. This is not the same momentum, but this is a reminder. It was this expression which is called P is equal to mv, but not m, because this is a wave, but just as a reminder. And the wave that is carrying momentum, when it hits a surface area, it also exerts a pressure, okay? So we have, it looks like we have huge disturbances which are caused by these fields. And now, very soon, we're going to talk now about the energy which is carried by a wave, and we're going to talk also about pointing vector. Pointing vector, it's a vector which is proportional to the E cross H, okay? So in essence, it looks like pointing vector, it points to the direction where the energy flow is going, So if we do here E cross H, what could be the direction of the pointing vector? What could you say? I can pick someone here in the class. So Besmiri has always talked. Bjorna, can I have Bjorna answer this one? So what could be the direction of the pointing vector? If the pointing vector, it is proportional to E cross H.
The pointing vector to get
That's correct. Okay, so most probably the direction of the wave, which is plus z, also the pointing vector should be plus z. And you can also extract it from here. So if it is E cross H, so this E, this is H, electric field, magnetic field. The cross product of AX with AY is going to be AZ. So it looks like the energy flow, or the energy that is carried along the direction of the propagation of the wave. So it is also both intuitive, so we can pick this up easily regarding the direction where the energy is carried from one place to another. Now, the next topic that so let's start. So this was a good example, good conductor example. And if you remember, the way that we have learned electromagnetic field theory, it was that you derive everything from the postulates, okay? And the postulates, they were simple: conservation of charge or conservation of some other quantity. It was just indicating a postulate which was never proven to be wrong. And from these postulates, we use vector calculus and you derive the Maxwell's equations. So now, the fundamental for us to start the analysis is the Maxwell's equations, and we know how we derive those. It was not difficult, we all did it. So the next, now from these Maxwell's equations, we have, for example, one of them is that the curl of H, the curl of magnetic field intensity, this is equal to J plus delta D over delta T. So we have the displacement vector and the rate of change is equal to this expression. Now from here, we see that the current flow, current density, J, which has a unit of ampere per meter square, okay? Because we know that J is equal to current I divided by area, cross-sectional area. So this is ampere divided by meter square. So this J is equal to the cross product of H minus delta D over delta T. Okay. So this was the current density. Then from here we can take the dot product with E. So we can take the dot product of all of these terms with E. And this is going to be equal to, again, let's try it like this for a moment. So the curl of H, what is the curl of H? The curl of H, it's a plane perpendicular to H. What we want to say is that the curl of a vector, which is pointing, like I have this vector, which is pointing perpendicular to this plane. Now, the curl of this vector is going to be perpendicular to this plane, which means that it's going to be the curl of this vector is going to be perpendicular to this direction, which means that it's going to be anywhere on the plane. Okay, so the result is going to be some vector pointing like this. And if there is some vector pointing like in this direction, we also know that electric field should have a component in that plane. Se ne dim që eja dhe h-ja nuk janë paralel, gjithmonë e ka një këmbë. Nëse curli I h-s e projekton rezultatin në këtë plan, me shumë mundësi dhe fusha elektrike ka një komponent në këtë plan, kjo do të thotë që edhe ky termi me shumë mundësi në shumicën e rasteve, ndryshe nga zero. Okay, so we get this expression here, and from here we can use, and this as a unit of watt per meter cube. So this is watt per meter cube because we know that actually if you look at this term, what is this? This is permittivity times E squared. Okay. So let's not forget that T, it was equal to this, and permittivity times E squared, we already know this one from the previous courses that we have taken, that this is an energy density, but this is Joule per meter cube. So this term, this has units of Joule per meter cube, but since we have also the time derivative, this is Joule per meter cube times 1 over second. Okay. Joule times 1 over second, this is watt, okay, or watt per meter cube. So this is what we see from here, from this expression at this point. And then And then we can apply some vector calculus here, and after we apply the term, we can easily obtain that E cross J, this is equal to minus H times derivative of P with respect to time minus E times delta D over time minus the dot product E cross H. Okay, so this is a new expression that we obtained. I can erase this one for a moment because it might confuse us. And if we look at these terms, this term here, this is the time derivative of 1 over 2 mu h squared plus 1 over 2. So this is the energy density, which is in an electromagnetic wave. So whenever we have an h, okay, if we take the dot product of h with itself, which in principle here, it appears like the dot product of the h intensity with the magnetic flux, with the magnetic intensity. This is energy density in a space. If you have Wi-Fi and also the cell phone working in your room, that means that for sure there is some waves which is coming from the antennas all around. You also need it because sometimes you need to activate your location in your cell phone. So you have everywhere some energy density, which is electromagnetic wave. It appears itself like this. And then, so here it looks like this is the energy density in a specific volume. And this term here, actually, if you look at this term carefully, this is the energy dissipated, okay? This is like the energy dissipated in the form of heat. So this looks like a term, I squared I, okay? So if you turn on a resistor, you're going to see that if you touch it, it will become hot very soon. And in fact, there are some components which are not optimized for energy consumption. Like if you go into your vehicle and you turn on the light at the top of your head, you turn the light, you leave it on for 5 minutes, if you touch it, it's very hot, because that one is not designed to be on for a long time. It's just to check something or to keep the light on once you get into the vehicle, especially if it is at night. But then you can really notice that it gets hot pretty soon, and this heat that it generates, it warms your hand, is in fact this term. This is not exactly equivalent, but at least in the car, it's not. It's a resistance that is getting hotter, but the units are the same. So this is energy dissipation, and dissipation is energy loss. And energy loss, the simplest way to happen is heat. For example, when you are in traffic, the vehicle gets very hot because all the energy is generated to the engine. Okay, so the car temperature increases. So here. What do we see here? We see that we have some energy loss, okay? And this energy loss is always related to some energy density, or the rate of change of the energy density. When we say rate of change, is that because we have the time derivative with respect to time, which means that as a function of time, the energy density is changing by this much, minus a factor that looks like this. Now, this factor, this is the way that the energy is carried by an electromagnetic wave. Okay, so in principle, we can even modify this by applying the divergence theorem. And how do we apply the divergence theorem? We integrate the expressions over volume. Okay, and this integral over the volume, it comes out to be a result of integral over the surface area. So finally, we can say that if we integrate this one, we're going to get the following. If we integrate this over a volume, E dot J, okay, dV, this is equal to minus d over dt This is again an integral over dv, and most probably should be like this because this was the unit of these terms. It was joule per volt per volume. We integrate with volume, we get joule. If this is joule over dt, this is watt. Okay, so this is power. So it looks like this is the unit of power. It's good to keep track of the different units, and then this is then equal minus the surface area. So this is an integral. This is integral over volume. This is integral over surface. And this is E cross H ds. Okay. So this E cross, now let's try, if we try to understand this again. So apparently, if this is watt, this whole thing. Okay, this is power. This term, this should be watt per unit area, watt per meter square, times, we have this other term here, the surface area is measured in meters. So this part, this is meter square. So you can cancel out the meter squares, and we find this expression. So in principle, what does this mean? This means that if we have a volume, so let's say that, let me draw this volume in the form of a sphere. We could draw this as a cube. This is showing the energy dissipation in this volume. Okay, so because we are integrating over this volume here. So here, if we have electric field, now assume that we have some electric field that moves like this, and some magnetic field which is located like this, but is propagating in this direction. Let me draw this with double red line. So this is, this is the H, this is the E, and this is propagating in this direction. It's going to enter into the system. So let this be the direction, and probably we get some J current densities which are induced. How are current densities induced in a material? Often, a current density is induced from an external electric field, and this would happen if the material is conductive. So if we have some non-zero sigma, which is the conductiveness, that means that we are generating some currents inside. If we have no free charges, if you have no free electrons, if it is a dielectric, if it is a piece of glass in your window, you get no currents. So that's safe that we have windows which have glass in there, because if that one was conductive, then the waves that come from the modem or the internet at our homes, or the signal that comes from the antennas of the cell phones, they will induce currents in the glass or in any material which is separating the outside with the inside. Then they will heat up. Okay, you'll see them warming, and then maybe they will even melt. That's not the case. Why? Because they are not conductive materials. So since they are not conductive, they don't dissipate energy. But if it is a conductor, if a sigma if this sigma is different from zero, you generate this. If you generate this, and this one is coming from outside, that means that you are going to dissipate or lose in the form of heat this much energy, and this much energy, which is going to increase the temperature here. So the temperature, which is measured in Kelvin, okay, this is going to increase in this system. This then is related to the energy loss as a function of time over this whole volume. We say loss because it's the rate of change actually, and there is a minus sign here, minus the energy that is passing through the outer contours. Okay, so imagine for a moment that if you have the energy which is in this case, in fact this is coming this way, and so this is like the point, this is the pointing vector, and over it can be that sometimes if the source of the wave, so you see this electromagnetic wave, in this case, tuacă mi vzatu, sigur antena povien nga jashtë, që do të thotë antena është jashtë shtëpisë. Por ne mund të kemi një antenë edhe këtu brenda, dhe nëse antena është këtu brenda, nuk e di si mund ta ndërtojmë një antenë. Nëse antena është këtu brenda, atëherë vjen që pointing vector do të tregojë që do kemi energji efektive efektivisht energjia del më shumë jashtë se sa vjen nga brenda. Po tjetër atë jashtë, ajo që është jashtë do futet dhe do dalë, efektivisht ky termi do kontribuojë në një zero, por mund të ndodhë që atë është brenda dhomës tonë, ose brenda ambientit ku ne do integrojmë, dhe kemi pak parasysh këtë integralin këtu e kemi në surface area. So this is over an enclosed surface. So this is the expression which relates the energy loss as because of the small non-zero conductivities in a specific material, how it is related with the energy density which is carried in the wave, and how this is related with the net flow of the electromagnetic waves in or out of a specific surface area, which is enclosing this volume. Okay? So we know from divergence theorem, right? We know how the volume and the surface area are related together. So this S, this is the surface area enclosing this volume which is inside. Okay? So this is called the pointing theorem. So this is how, and the pointing vector or the power density, we define it with, I'm trying to find a place. So we define a vector which is called the power density. And power density S, this is equal to E cross H. And let's have a look. What is the unit of power density? So we can see from here, the power density is measured in watt per meter squared. So we learned a new quantity which is shown or defined like this. Now, if you'd like, we can have a short break and we can continue after 5 to 10 minutes.